Hello and welcome to the Norwegian Academy of Science and Letters, where we are here to celebrate the Kavli Prizes 2024. My name is Adam Rutherford.
And I'm Vivienne Parry, and this is all part of a week of science celebrations for some of the great breakthrough discoveries in the field of astrophysics, nanoscience and neuroscience. The biggest, the smallest and the most complex.
Yep, and we're in the rare position of having all of the laureates, all 8 of them, in the same room at the same time for the first time. So we brought them all together for a chat, to have a discussion about the nature of science and about the nature of their work, and for you to get the opportunity to hear what scientists talk about when you stick them in a room together.
Yeah, the great thing about the Kavli Week is the conversations that you hear about science and between scientists. So as Adam says, we've got all 8 in the room with us today, and we're going to ask each of them to introduce themselves to us with a one-line summary. Very difficult. Over to you, Sarah Seager.
I search for aliens, non-humanoid, non-intelligent, life beyond Earth.
Chad Mirkin. We work on taking the basic building blocks of life, short snippets of DNA, RNA, peptides, and proteins. We restructure them on the nanoscale to develop powerful new forms of medicine.
Bob Langer. I work on creating new materials to deliver drugs and vaccines, often through nanoparticles, and also on creating materials that can help create new tissues and organs like artificial skin for burn victims.
Paul Alivisatos. I'm in love with the study of very tiny crystals, the smallest possible ones called nanocrystals, which are used quite widely in biomedical imaging.
Doris Tsao. I'm trying to figure out the mystery of how billions of tiny neurons work together to generate our conscious perception of the visual world.
Nancy Kanwisher. I use brain imaging in humans to try to figure out the structure of the human mind.
Freiwald. I'm working towards understanding what it is about our brains that makes us smart.
I'm Dave Charbonneau, and I develop new methods to discover planets orbiting other stars and to study their atmospheres.
Well, there you go. So wildly different disciplines. And we're going to start with the biggest. So with Dave and with Sarah, exoplanets, so planets outside of the solar system. Now, when I was an undergraduate back in the 90s, there were 9 planets in the universe, and then it went down to 8. Sarah, what are we up to now?
Thousands. There are over 5,000 exoplanets with thousands of more waiting to be confirmed, and likely trillions in our galaxy alone.
So the existence of planets is pretty much universal. Wherever we find stars, we find planets.
Mostly. Mm-hmm.
So what changed since 1990-something?
Well, one thing that happened was nature was very bountiful and created planetary systems so different from our own solar system that ended up being much easier to find, like a giant planet where Earth should be, or planets interior to Mercury's orbit. And our techniques, designed for binary stars, ended up being able to find these planets in multitude.
What were those techniques? What were the technological developments that allowed you to suddenly see so far beyond the solar system?
Well, many of them were just detectors, the same advance that gives us our detectors in our phones. There's computer power that enabled us to sort through signals. So all the same things that have benefited the rest of us helped in astronomy.
That we can see through our phones?
What do we see through our phones? I just mean you now have this incredible camera on your phone because of the detector. In the old days, we had something called the photomultiplier tube, where photons would enter and you could look at one star at a time. The CCD detectors and others like it gave us way better sensitivity and bigger areas to look at more than one star at a time.
Dave, when the field was emerging, it's completely new territory. We're looking so far beyond the solar system. People must have thought, well, why are you doing this? Is this even possible? What was the attitude like to you setting out to look for exoplanets?
I think there was always a fascination in the question of whether there were planets orbiting other stars and whether there's life on those planets. The trick is we had convinced ourselves that all other planetary systems would look like our own. And so what does that mean? That means that the biggest planet, the one that's going to be easiest to find, is Jupiter, and that takes 12 years to go around. And so any planet hunter would naturally be setting out on a 20 or 30-year effort. And of course, what happened is that nature was just incredibly creative, and it turns out that there were some planets on very tight orbits. And so once astronomers approached this challenge with a more open heart, a more open mind, then they could find all these worlds.
It wasn't that people didn't believe planets had to be out there. We've seen stars forming with disks that surely ended up with planets. It was mostly that it was such a hard project because the planet and star are not spatially separated with our techniques. So you have a massive, bigger, brighter object next to something tiny. So the skepticism and laughability were just how hard it was. Why would you try the impossible?
Did you get people, you used the word laughability there. People thought it was a joke?
Well, not a joke, but in science, we have something we call the giggle factor. If I tell you what I'm working on and you start laughing, or you have to suppress the laugh, it's in a totally different category than something taken seriously. So it wasn't taken seriously because it was perceived as too hard to do, too hard to find lots of planets, too hard to make progress.
And I mean, in terms of the scale, you're looking for like individual pixels going in front of a light source?
Oh, it's a very subtle signal. So, for example, the first way the planets were found was by measuring the wobble. Okay, so that the idea is the star is going to change very subtly in terms of its speed. It's going to come towards you and away from you. And of course, that's due to the gravitational tug of an orbiting planet. What that means is that the shift on the detector is 1,000th of a pixel or 10,000th of a pixel. So I think it's fair to say that many times in grad school, and Sara, you probably experienced the same, we were told, oh, the things you're thinking about, that's all well and good, but you will never be able to measure those signals. That was really kind of a drumbeat message.
And even when we made the prediction and the follow-up and did measure it, then it became, this is a one object, one method success. So even when we did do it, the feeling, the thoughts, the belief was that there won't be enough objects to make it a field.
So how did it go from just finding, one of those, fraction of a pixel to, you said there are thousands characterized and millions waiting to be characterized?
Well, there's different levels of characterization. There are thousands of confirmed planets. That means they have a measured mass. There are thousands more that are known to exist. They have a measured size, but not a measured mass. And I said, we just extrapolate to there being, that every star has multiple planets. And given that our galaxy has hundreds of billions of stars, and the large majority of those stars have an entire planetary system, that's how we get to trillions. Following? Yeah. Trillions of planets are out there. But how did we get from one to more? Well, typically in exoplanets, when we found one in a category, it would be the tip of the iceberg of many, many more in that category. So if you find one, then people knew better how to look, how to find them. So when we knew there were planets very close to the star with 4-day period orbits, not 12-year, and we knew the drop in brightness was 1%, people could then create surveys to directly searching for that specific object and then find more and more.
And the diversity of the solar system itself, so we have Earth-like planets, but we also have gas giants, and Pluto was a planet that has now been relegated to be, what is it, a dwarf planet these days?
Dwarf planet.
Yeah. So does the diversity within the solar system help you understand what type of planets might be out there, or is there more diversity?
No, there's far more diversity out there than in our solar system. In fact, planets appear to exist in every mass range and size range and orbits that are physically plausible. So I like to say anything is possible within the laws of physics and chemistry as far as exoplanets are concerned. It's astonishing.
And the popularity of this field beyond you guys as researchers is enormous. It's fueled by science fiction. Where does your sort of outlook on what you're studying, how does it overlap with how we view the universe through fiction? Dave, I know you're a big sci-fi guy.
Yeah, I was the kid that grew up watching Star Trek, but I also watched all the launches of the NASA space shuttle, and I think that I definitely dreamt of, wondering whether there were planets orbiting other stars and life on those planets. So I think that, while my approach has gotten a lot more technical over the years than that sort of dreaming, I think my motivations initially were the same that, humans have always wondered if there's life on other planets. And that's what brought me to the field as well.
Well, you just introduced life. And Sara, you said you were looking for non-intelligent life in the rest of the universe. So what are you actually looking for when you're surveying the skies for different planets?
Well, before we get there, we often get asked the question, do you believe there's life out there? What are the chances? And I like to say we're getting there. we're first finding that there are planets. There are lots of planets. It's a legit field. There are planets. Next, there are planets the right temperature for life. And that is the next step. Now we can say we're trying to understand their atmospheres to understand the surface temperature, which is controlled by the greenhouse effect of the atmosphere. We're looking for planets with water vapor in the atmosphere that might indicate a liquid water ocean that could support life. So that's the step. Those are the steps we're taking. And after all of that, we'd like to see gases in the atmosphere, gases that are associated with life, like oxygen on our planet. And it's going to be very tricky to do that because we have to understand that gas in the context of false positives and the whole planetary environment, which is very hard to parse.
If we were on Mars right now or another planet in the local neighborhood, would we be able, with our current understanding of life and our current technology, would we be able to detect life on Earth?
It's a great question. And it turns out that Carl Sagan did this experiment when the Galileo spacecraft was en route to Jupiter but had to do a flyby of Earth, turned the instruments on, pretended knew nothing about Earth, and tried to do this experiment. And the answer was maybe, but maybe on the side of yes, maybe. Because there's oxygen in the atmosphere together with methane, they shouldn't coexist. Although for exoplanets, it may be hard to see both at once. They saw a sharp rise around between 700 and 800 nanometers that is not associated with any known mineral. That turns out to be associated with the red edge of vegetation. And so they made a list like that. But it was still very difficult to say yes robustly.
And the type of life that we would be looking for, we only know of one type of life, and that is life that exists on Earth. And it is a universal tree. It all shares proteins and DNA. It has one single root. Presumably, life in the rest of the universe would not necessarily resemble those molecules.
Not those molecules, but we're assuming that some life out there has to use chemistry like we do. Chemistry to extract energy from the environment, to store energy, and to use energy. And in using energy, generate a byproduct, gas. So we're making that assumption. We're not assuming DNA, we're just assuming chemistry at large.
Okay, so when is it going to be? That's the question that scientists hate being asked, but we have to ask.
Right, well, there will be announcements and have been, but they'll be very controversial until we can get to the future.
I mean, I want a date.
Yeah.
I want a precise time and date. No.
I mean, there's going to be a time when we can say we have a sign of life with an associated probability.
Mm-hmm.
So I'm sure people will and have been doing this, and there'll be like a 1% chance it's actually right. We probably shouldn't say it out loud at all, but it happens. But when you want to get to, say, 90%, it's still probably a ways off.
Did you both feel, as you were going through this process and realizing you're in a very exciting field, we're talking about life in the universe, one of the biggest questions that humans have always obsessed with. This research requires funding. You've got to go to the funding agencies, all scientists do, and say, can we have money so that we can look for life in distant galaxies, proper Star Trek style?
Mm-hmm.
What is the reaction from the funders? Do people take you seriously?
Well, I think that like all good science proposals, you point out the long-term benefit, and then you make a case for the incremental thing you're going to do. So I don't write proposals saying I'm going to go find life and I need a 3-year grant because it's going to take me, 2.5 years to do it. I say, look, here's what we need to do. First, we need to find the planets that life might be on. Then we need to understand what gases they might produce. And then we need to actually go and detect those gases. And I just want funding for that first step. And I think that the funding agencies do they're very concerned with how realistic your proposal is. But they've been very supportive of I think they understand the need for research, for investment in those basic fundamental questions that drive us.
So as Sara says, the line between mainstream and crazy is constantly shifting. And actually, you've got the benefit of timescales in astrophysics.
We do.
She says controversially, because, it's going to take hundreds of years before anybody knows whether you're right.
You mean that someone has some more direct way of confirming that there's life on other planets?
Yes.
Well, yes, I think realistically we may never, in any realistic way, travel to these other places. So it is a profound question to ask whether any data set, any spectroscopy, any study of the light from other planets and the properties of those planets would allow you to conclude that it has to be uniquely life and couldn't be instead explained by geology. I think that there is a case to be made that with good enough data, we would have to point to biology as the origin. But that's an actively debated question in our field.
We all remain absolutely fascinated. But let's now go from the biggest to the smallest. What I'm hearing from both of our speakers in astrophysics is about risk-taking, that you're looking at things that nobody has ever been to before. And each of our three laureates in nanoscience have all described entering completely new fields. And I wonder what was that was like for each of you. So Bob Langer, just tell us what area you went into.
Well, I'm a chemical engineer, and I guess when I finished my degree, which was 1974, by far the most common thing for a chemical engineer to do was work in an oil company and, make better oil or make better, isolate, petrochemicals and things like that. So I certainly thought about doing that because that's what, a lot of my friends and colleagues did. But I wasn't that excited about it. I was looking for some way, and not that I really knew, of trying to help people, to try to, I guess, do some good with chemical engineering, in my opinion. And, I tried to get some teaching jobs. Nobody would hire me. I then started to think about, medicine, and nobody would hire me there either. But finally,
it's like turning down the Beatles, isn't it? If you're a record company,
well, I don't.
Bob Langer.
Well, I'm not so sure about that. But Beatles are a pretty high bar. But then finally somebody said to me, there's this surgeon in Boston named Judah Folkman, and he said sometimes he hires unusual people, and he was, and so they suggested I write to him. I think the person who said that, thought very highly of Dr. Folkman. I'm not sure what he thought about me. But anyhow, I wrote to Dr. Folkman, and he offered me a job. So I went to a hospital. I was the only engineer there. So it was very different. And it was difficult to learn a lot of those things. But eventually I did learn some things and went from there.
You were taking a risk, but you also had somebody who really trusted you. I mean, Judah Folkman must have seen something, and then he allowed you to the space to get on with doing something, which I think in those days was blood vessels and cancer.
Yeah, I think that's right. I mean, he'd take chances. A lot of people always want to hire somebody who's got and especially then, a lot of people would want to hire somebody that would have the exact right background to do what they'd want. In that case, it would maybe be a biology background. He felt that people had tried doing that in standard biology for a long time and not succeeded, so he thought maybe somebody different might do okay.
And Chad, you also say that you are a risk taker.
Yeah, I mean, I think if you work in the field of nanoscience, you have to be, because I was trained as a chemist, and the one common theme of nanoscience are people crossing boundaries. It's a field that involves science, engineering, and medicine now in a very significant way. And nobody is trained to know all those areas. So you have to be willing to go across the boundaries and engage with a lot of people you normally didn't engage with, and ultimately find a path to do the things that you want to do.
And what about when you found these things, these spherical nucleic acids that have kind of bits of DNA stuff?
Well, that was great. I mean, so that's a beautiful example of, you take the blueprint of life, and we know what it is as it's made naturally. But with nanotechnology, you can take short snippets of DNA and RNA and restructure it on the nanoscale, transforming it into a spherical form. And those forms turn out to have properties that are completely different from what we associate with normal DNA. And those properties end up being enabling. That happened because I had a colleague who actually invented the tools for synthesizing DNA, a guy named Bob Letzinger. And I had this idea of interfacing DNA with tiny little particles to create programmable atoms. And I asked another colleague, I said, how can I get my hands on some DNA? And he said, well, you can either order it through these garage operations, or you can walk upstairs and talk to the guy who invented it. So I did better. I sent my postdoc over to talk to him and say, how can we make some DNA that we can tack onto a particle? And that really got us started and launched the whole field.
But who was the person who supported you to take that risk? Because it was a leap, wasn't it?
Well, they're supporters, and they're also stone throwers. So you run into both. And I choose to work with the supporters. And I had great people that believed a lot in what we were doing. But it wasn't like everybody was saying, wow, Chad, let's go. A lot of people.
So you've got to ignore the stone throws.
Yeah, when you move into a new area, when anything is new, although I think scientists are generally good, there are people that don't like change, that they resent the idea that fields are moving in new directions. And some people embrace it and others resist it. And you have to kind of fight through that resistance.
And I suppose in some regards, science has made through these great leaps forward. We sometimes call them paradigm shifts, although I don't like that phrase particularly. But there's also science which is done by like little incremental steps. You know, it's chipping away at the coal face. How do you find that if you're asking big questions, you have to do both? You have to balance the big with the incremental?
You need both groups. So you need people that are builders and chipper awayers, and you need people that do something radically different. And it's a combination of those two that ultimately leads to big discoveries in the development of fields. That's definitely true in nanoscience.
And Paul Alivisatos, your field is kind of quantum dots is what we know you best for. But the thing that was also a kind of risky field, and you were first in there. But the thing that supported you is that you were given tenure years ahead of perhaps the normal run-of-the-mill graduate, because people could sniff this new field and thought that you were the one to take it on.
Well, it's a little bit like the stories that you're hearing from the others. When I first got involved in studying very tiny crystals at Bell Labs, and there, at that time, the production of electronic quality, the best semiconductor materials, was done with very complex technologies that involved vacuum apparatus and certain kinds of very controlled environments. And we had this idea that you could make equivalent or even possibly better quality materials by growing those materials in a liquid to make very tiny crystals. And there was, in fact, a scientist, a very senior theoretical physicist at Bell Labs that I visited with some of our early data. And it's still very memorable to me that he said, he looked at my results and said, you seem like a very nice young man. You really ought to go work on something else, because this is not going to pan out for you. Actually, that was a kind of gift, because getting pushed that way made me go back and try to think, well, in principle, should this be able to work or not? And then that resulted in us doing lots of experiments early on in my time, as a beginning professor at Berkeley. And in fact, during that period, there was no funding for this. It was an obscure topic, and most people thought it probably wouldn't work. And so I wasn't getting any financial support when, in fact, but we were starting to publish our early results and showing that actually, in principle, the tiny crystals can be made more perfect than the large one. It was exactly the opposite of what the person, who had been pushing on me was saying. And I'm just very grateful that during that time, my colleagues at Berkeley, were studying. They were following what we were doing, and they came to believe in it. And they said, okay, we're going to back this kid. And so it worked.
And also you had a very supportive funder, I think, as well in the Department of Energy, didn't you?
Yes, the Department of Energy, the Office of Science. After some of our early work came out, they became convinced that this could become something useful. And so they stuck with us for a long time. And I don't think we could have had the success we did without that support.
And we celebrate the basic sciences in the Kavli Prizes every 2 years, but this is an area which has so much translational potential. Those early experiments with inventing new DNA, new types of DNA, and what all three of you have done. You must, all three of you, have been thinking there's a thing at the end of this which is going to serve humanity through medicine or through other technologies. Was that in your mind, Chad?
I think that's a big part of what we do. There's probably combined over 2,000 patents that are associated with the three people here, and those have led to an enormous number of technologies that now are impacting people all over the world, especially in the field of medicine, but other areas as well. So yes, I learned early on, I said, if I'm going to get involved in the field of nanoscience, one is I want to do it right, I want to do it big, and I want to make sure I focus not just on the science, but the technology, because it's called nanotechnology for a reason. So how do you take these discoveries and translate them into technologies that impact the masses was a big part of how we built things at Northwestern and how we practice nanoscience today.
And Bob, how do you feel about, and throughout your career, felt about how you distribute the spoils of this research? Because science is for humanity.
It became very important to me. There was a moment, for example, when these things we demonstrated their first uses in biological imaging, and so many people wanted then to be able to build on those results and to be able also to test them and to do their own work. So we did very quickly make the decision that commercializing this was the best way that we could get these things out there. And so we moved very quickly. Within about a year and a half of our earliest demonstrations, there were commercial products out there that allowed people to use the materials. And also, again, working with Department of Energy, I felt very strongly that we needed a place where people who were developing new nanomaterials could share those results with others in a lab-to-lab fashion, not just through selling products. And so we created something called the Molecular Foundry, which to this day has hundreds of scientists in it who advance making new materials. And their mission is to share that with other people as quickly as possible, to have them come and visit their laboratory, see how to do it, not just read it in a paper where sometimes it gets lost in translation. And those two mechanisms, where it was appropriate to go commercial and where it was appropriate to go to a sharing mode, I'm very glad we were able to do those things, because it made it part of a whole community that could then advance the area much more rapidly.
And Bob, Chad was talking about naysayers. Now, you set up Moderna, which we now know for the mRNA vaccines and the COVID vaccine in particular. It saved millions and millions of lives, and yet there are people now who rail against the vaccines that were produced. How does that feel for somebody who's set out to do good in the world?
Well, I'd rather they didn't, but, it's a world where, you want people to be able to say what they feel. I guess my hope is that by doing good science, by publishing that science, and that people will ultimately look at, and I think the majority of people still do, that those vaccines have saved millions of lives, and that future technology built on that or others will continue to do so. So, I mean, and I should say, I'm to your question, I've had people be naysayers my entire life, and they said, you can't. They said these things that stop blood vessels don't exist. They said that to create molecule delivery systems, which would ultimately lead to things like Moderna and others use, said that was impossible. I mean, all these grant places, would turn us down for years and years and years. So I'm pretty used to it.
But could we also just, if I may, so the role of skepticism. So here we're talking about these prizes, and where people had they had a passion, they thought something was going to be true, others pushed back against it, and so the premise, I think, of some of the conversation is that there were the kind of the good people who had this kind of persistence, and then the kind of questioners who were perhaps either naive or ill-intentioned. I want to come back to saying that this is what science is all about. It's healthy to have skepticism, and it's healthy to push back against it, and to take that skepticism and say, I'm going to internalize that and try to see if it is right or wrong by testing it, by pushing back against it. And that kind of tension, it can be hard, but it's the way of truth seeking. I mean, it's part of how science advances, and so every big advance will have this story with it, where people pushed back, and then ultimately underneath it, you'll find there is that something that the initial assumptions weren't right, and it's healthy. It's just part of how we advance.
It's very interesting listening to you guys talking so far, because even though astrophysics and nanotechnology, nanoscience are quite distantly related fields within science, I can see themes emerging, talking about skepticism, talking about trust, talking about the naysayers and the process of anti-doctrinal thinking. But we haven't talked to the neuro guys yet. Before we open it up to talk about those broader links. So let's just get a feel for what the Neuroscience Prize was for. Doris, Nancy, Winrich, congratulations. Nancy, can I start with you?
Sure.
How we perceive the world is obviously enabled by the things that we're using right now, our brains. We wouldn't be able to do any of that stuff if we didn't have brains that function. But your interests, they started long before you were thinking about faces and those areas of the brain. How did you get into thinking about how we perceive the world?
Well, in graduate school, we didn't have brain imaging tools. And so I studied vision just by measuring behavior. It's kind of like trying to figure out how a car works just by driving it around, or finding a car that's broken down and figuring out the ways in which cars break down and trying to infer from that what goes on inside. That is an impressive field, and you can do a lot that way. But once you are able to open the hood and look inside, it's hard not to do that. So my first year in grad school, the first brain imaging study of human visual cortex was published on the cover of Science. And I just looked at that and said, wow, must do that. And it took me a decade to get access to the machines to be able to do it. And in between, I spent a lot of time studying vision by measuring behavior. But it is just so tempting and so vivid to actually see the brain in action and watch parts of it turn on and off.
Do you feel that it's very much a technologically driven area of science, that our ability to see things we've never seen before is enabled by the tech?
Oh, I think there's no question that science advances enormously when there's a new technology that comes along that enables you to see things you couldn't see before. You know, the kinds of questions that we address in my lab are questions you can't address with behavioral methods, but it's absolutely game-changing to be able to watch brain activity in normal brains non-invasively.
Doris, I love the way that you described what you do as being, trying to relate the perception of the world to the trillions of microscopic neurons sitting in our head. How do you manage to hold on to those two things simultaneously? You've got to ask a simple question about perception, and you've got to relate it to how our brains are actually working and how they're structured.
Yeah, I mean, that's the miracle of the brain, that there's these tiny neurons all with limited computing power, and then they can give rise to this representation of the world. So, we don't know how that works. And the beauty is that you can study these single neurons and just listen to how they respond to a variety of visual stimuli, and you can actually make sense of it. So, we got this prize for figuring out how these neurons work together to represent the identity of a face. And it turns out that they're using this quite simple code that was originally discovered in computer vision. And knowing this code, we can actually understand what each single neuron is telling us. And if we put all the messages together, it turns out that we can actually reconstruct the face that a monkey is seeing, like almost perfectly. So you can't even distinguish the actual face from the one that you reconstructed. So the code of the brain really is understandable, and that's what we're trying to do.
And it's such an important part of evolution in general. Animals have faces, but one of the things that your work is broadly involved with is actually identifying that such a significant part of the brain is devoted to facial recognition. So this is, as you say, it's part of our identity, but it's really part of being what it means to be a human.
Yeah, so Nancy did the pioneering work showing that these face areas, which initially lots of people were skeptical if they were actually face areas, are really specialized for faces. And then Winrich and I went in with an electrode in the monkey counterpart of these face areas that exist in humans, and we found this astonishing result that almost every single cell in this region responded much more to faces than other objects.
So I remember when this work came out, because my background's in vision as well, and I remember thinking, I'm surprised that this area is so localized, because we've gone from the 19th century when everyone said this is the area that does this, to a much more distributed understanding of how the brain works. And then suddenly in the 2000s, you went, oh no, this is the face area. So how am I misreading this, or can both of these things be true? Winrich?
I think we've all been surprised as well. We have different backgrounds in science. My background is information processing in the brain is distributed. And so I initially, when I first heard about face areas existing, I actually thought this is something that that is really weird. That there would be like these highly specialized regions because you wanted like a general solution, right? And so I did not expect it, but Nancy's findings were very strong. And then when Doris and I saw the cells, almost all the cells being phase selective, it was just a fact. And so now you have to think about like why is it organized in this way, and the different ideas about why this might be.
I would just want to add that there's two different claims here. The claim I think that the three of us would make is that those face processing regions are very specific for processing faces. But that doesn't mean that that is the only part of the brain that's necessary. Of course, you need eyes, you need the whole visual pathway that leads into that, and you need the whole rest of the brain to read out those signals, or there'd be no point in doing the computation. So a lot of the brain is involved in face recognition, and our point is that there are a few little bits that are highly specialized for it.
Well, as we begin to broaden the conversation out, so we're all talking about our different fields with each other and some of those emerging themes. Did you guys find, you're discovering that you thought it was distributed, but actually Nancy's showing that it's highly specialized or highly localized. What were the naysayers? What were the skeptics? How are they responding to you guys finding out that there's these really, really highly specialized? Doris?
I think that our evidence was incontrovertible, if I may say so. I mean, we can just see all the neurons from this area, and every single neuron responded more to faces.
Yes, that's true. I did not have that experience. I have experienced pushback all along. In fact, last year, two major people in my field published two different review articles saying, of course, we have moved on and we now understand the brain is not composed of specialized processors, but everything happens everywhere. And I read these papers and I think, could you please engage with my data? So it's very strange. The debate continues despite the evidence we have.
I think the experiences are partly different because of different technologies. fMRI, the technique that Nancy used, is an indirect measure. And so people, would have arguments saying that, well, it's an indirect measure, the neurons really phase selective. Then we went on to show the neurons are really phase selective, so it's more of a fact. And questions that did come up are, are these boundaries of these areas really sharp, and, what exactly is happening inside these areas. So I think those were the skeptical comments.
Paul mentioned the naysayers being a part of science. Skepticism, doubt is a cornerstone of science, but I suppose it's how it's phrased and how it happens, because science is competitive, but it is also collegial.
So I think naysaying is extremely important, and absolutely, we should listen to our colleagues when they don't buy our results, and we should be our own, devil's advocates, trying to think of alternative accounts of our findings. What makes me cranky is when people push back generically without engaging with the data.
But then you've got to be in a position like Doris said, which is, the data's incontrovertible. Incontrovertible is a strong word.
Yes.
I like that.
But it's tough for the public because argument is the way that science advances, but actually the public see that it's you all changing your mind. And that's very hard to get across.
But scientists must change their mind. If we didn't change our mind when we saw new data, we wouldn't be scientists.
I mean, you're preaching to the converted here,
yeah,
Nancy. But it remains a fact that the public see this as a big, big issue and think that it means that one side is wrong and the other side is right, where in fact it's part of a process.
I think that means we're not doing our job well enough communicating to the public about how science works and what it means to make a claim and to present some data and show how it supports the evidence. Because when you do that, of course, there can always be new data that overturn that claim. That's the nature of science.
It's very interesting to hear you specifically say that, because you've had a dual career as both a research scientist and also as a science communicator, as a journalist. What was it that made you sort of tread both those lines?
Well, it's kind of you to say I had a career as a journalist. I would put it differently. I dropped out of graduate school several times because my experiments weren't working, and I thought I'll do something important. I'll try journalism. I didn't make it in journalism, but I do think it's very important for scientists to communicate the results of their research to the public. The public pays for what we do, and I think there's multiple different contributions that science can make to society. Some of those are the applications that improve the quality of life for everybody, such as the nanoscientists here do. But other parts of science are just, like revealing fascinating new facts about the universe that we inhabit and the nature of the human mind. And these are things that just are thrilling to learn about. And they're thrilling to everybody if communicated properly. So I think it's our job to share that thrill.
Sarah.
The nuances are certainly very, very hard to communicate because in our case, the public would like to know, is there another Earth or not? Is there life or not? And sometimes we're just taking those stepping stones we tried to tell you about, but it's not a black and white scenario.
But the point is that they all queue up outside any astrophysics presentation. They're all there, queues and queues of people. And the public really understand astrophysics, but they see its importance, even though the timescales are so long.
It's true, but we also say the sky is for everyone, and everyone can go outside and look up and wonder what's there. And that's why it has such a broad appeal.
What about the problems that you have in nanoscience, Bob?
You mean in communicating, or? Well, I was even thinking as Nancy was talking. The major way that I think at least I communicate, and is writing scientific articles and then giving lectures. But that doesn't reach that many people. I certainly talk to the press at different times if they ask. But it's the media that really like the journalists or whoever, TV, that reaches the masses. And I don't know. And some of them are very good. Some of them are not very good. Some of them want to stir controversy, But I kept thinking as you were talking, how, especially I didn't even realize that you had studied journalism. But how did they reach? I remember one time I had some interview and from one of the scientific journals. She said, well, why did you take the time to talk to me? I said, you'll reach 1,000 times more people than I will. So I'd always do that, But I don't know how you change that.
I think one thing we can do as scientists is just make an effort to take every opportunity to give talks to lay people. And something I've done at MIT 20 years ago started something called OpenCourseWare. This is before Coursera and edX and all of that. And they just started putting all lectures and course materials online. And a few years ago, I took my course lectures and put them online. And within a few months, I had 10 million views of my first lecture. And that to me is so thrilling. I get emails at least once a week from people in remote parts of the earth who are so excited to learn from an MIT professor about the brain. They're just thrilled to bits. And that makes me so happy. And I think it's a really important thing we can do.
I teach a science communication module at my university. And I had a student last year. I was teaching how to make videos, how to talk about your research. A young Chinese student said, I've got my own YouTube channel. 9 million subscribers, and I thought you should be up here instead of.
But can I say that one of the great joys of my life was going into MIT with the BBC, and every door was opened. Hello, come in, sit down. Let me tell you about what we're doing. And whatever subject it was just so engaging and so interesting. But I guess we've got polarized in our views about science. And Nancy, in the speech that you gave at the banquet, the formal banquet at Kavli, you were talking about fraying of trust with science.
Yes, well, I do worry that currently we're facing a large faction of people who do not trust scientific results. They're skeptical of vaccines. It seems like a real problem we have in society, and I don't know what we as scientists can do, but I do feel it's our job to work on this and try to address this.
Chad?
Actually, I have a different view. I think it's healthy. I go back to what Paul said. I think the biggest mistake that's been made in terms of the interaction between scientists and PR is the idea that this is right because scientists have told us it's right. Science is not always right. Scientists always get it right. Over time, it'll eventually be taken to the right answer. And this issue of questioning, even where you think you have it definitively understood, I think is a good thing. Over time, we'll figure it out. And if no new data comes up that contradicts it, then that will be the message of the day. But there have been many examples throughout history.
That's where the nuance comes in. Like if it's for the measles vaccine, you want kids to get that vaccine.
I understand.
I mean, lots of people died by not getting the COVID vaccine.
But you want that nuance to come in of what is, on the scale of what we're figuring out versus what we're confident at a high level of.
But that sounds like a science literacy problem more than a trust problem, because if you work under the principle that the publics, because there are many types of public, have a level of scientific understanding that they can process data and understand statistics and understand the scientific process enough that they can analyze what is being presented to them and say, yes, obviously vaccines are the most effective medical intervention in history, and therefore we should have some faith that they have been tested to the point that we know they work.
Let me give you an example. So we developed vaccines for COVID as well. And we develop a new vaccine, we test it against a control, no vaccine. And you give the animals, in this case, a lethal dose of COVID, so they all should die. Every animal that got the vaccine lives, every one that doesn't die. That does not mean that it's perfectly safe. But it does mean if I'm a betting person, I'm going to bet on taking that vaccine. So I think the way you argue and the way you tell people, it's a risk analysis, and the risk is relatively low and the benefits are very, very high. And I think if you communicate that properly, you get better buy-in, as opposed to there is nothing wrong with this, you should take it under any set of circumstances. That's where people begin to push back.
Dave, we're talking about probability. I mean, Chad's using betting analogies, but we're talking about probabilities, really. In astrophysics and search for extrasolar planets, we are talking about major probabilistic questions here. What do you think the literacy of statistics and probability is like when we look at the stars?
You mean among the general public?
Yeah.
I think it could be better. I mean, but in a good. I mean, it's probably better now than it's ever been, to be honest. I mean, we shouldn't, But I think that I have children. I've watched them go through the public schools, and what I see is a curriculum that's very focused on teaching topics in science. So understand the Earth-Moon system. Great, that's really important. Or understand, anatomy. That's very important. The more subtle thing, the really tricky thing, is understanding the real scientific method, not the formalized one that sometimes gets trotted out. And part of that is statistics and probability, and understanding that your confidence in some claim can wax or wane with new data, and it's never 100%. And I do wish we could engage more in that subtlety, and that it's very natural to be uncertain and to say, well, I'm pretty confident, but I've gotten some more data and now my confidence has decreased. But that doesn't make me a sloppy scientist. It makes me a great scientist.
Doris.
Yeah, I'd just like to say that as a vision scientist, it's actually a really interesting mystery why our perception of the world is always one or the other, even though the inputs are always probabilistic and ambiguous. If you've seen the space-phase illusion, you either see it as a face or two faces, or you see it as a vase. You don't see in between. And so that's something about the brain makes us just not be able to deal with uncertainty and to pick one interpretation or the other. And it's a very interesting problem.
You see what she did there? Neuroscientists always bring it back to the brain. Always, always. I wanted to move us on to something that all of you have mentioned in the splendid biographies, which, if you want to look at them, are available on the Kavli website, which is about mentorship. And we've been talking about trust. A lot of you were given enormous levels of trust by mentors, by colleagues, that actually meant that you could proceed in your career. Paul, how was it for you? How were you trusted? And how do you make sure that trust is available for your students now?
Well, it's interesting that you say that. I think you're basically right that it is a theme that in the midst of tension around skepticism, that somebody coming in and creating a protection and saying, okay, go ahead and try this, that's a very big, important thing in science for that to occur. And it does occur. Most stories that you hear where somebody had a dissident idea and then it turned out to be true, somewhere in there were people helping them to do it, even if they were themselves skeptical. So I think it is a really critical piece of it. I also want to come back to something that I think you referred to when you described visiting MIT, and Nancy, I heard it in your voice a minute ago, which is that scientists do have a sense of beauty that, or something that they're pursuing that means a lot to them. Their sense that when they're looking at something and seeing something others haven't seen before, that really means a lot to them. And I think the way that many of us gain trust is by showing that we care about something very deeply. And it's enough that someone who has some power will say, okay, if you believe in it that much, I'm going to give you some space to try it out, while others are kind of questioning it. And that's just a really good system. It is why science moves so quickly, because it has this dual element of trusting on the one hand and really not trusting on the other, and putting those against each other and seeing what will emerge. It's a beautiful thing.
I love the idea that you're seeing something for the first time, and that should be an inspiration to scientists. I also think about how the characterization, the stereotypes of eureka moments in science almost never happen. But I want to ask you two, though, there must have been a moment where you saw something in your data and thought, hold on a minute, I may have seen a planet that no one else has seen.
I mean, I definitely had that moment. I was working with my advisor, Tim Brown. I'd gone out to Colorado, and we had a small telescope in a parking lot. And we gathered data, and I remember sitting in the office and analyzing it and really seeing that signal for the first time. But even then, it's this deeply uncomfortable thing. You're looking for a thing, you see the thing, and then you worry, did I make a mistake? Is it really true?
Did I see the thing because I wanted to see the thing?
And I did want to see that thing. But then of course you test. And
you test until you get to Doris's point where the data is
incontrovertible.
Yes, beyond the shadow of a doubt.
Yeah.
So I was really fortunate as a student to have that.
There's another related space of having a new idea and having to work out that idea to see if it's viable. That's like if you're climbing a big mountain, at some point you're going to summit. And you're like, so I've had these moments where after a lot of time working out the idea, having the moment when I know it's going to work out. And that's an amazing feeling.
There's a quote that you wrote, Winrich, from Kant in your biography that you wrote, which was sapere aude, to have the space to think. I feel like we really need to encourage a culture in science where we do have the space, especially to give younger scientists just time to really ponder those questions.
I agree. So I meant it as a statement about society. I think we profit from a free society that allows us to think freely. But I think it also applies to mentorship. And I think the main advice that I would give is find your own voice. And that includes being able to think for yourself.
And Doris, you said it in your biography as well, that you spent 3 years chasing down my fantasies with complete freedom. I think many scientists don't have that complete freedom, but that's great.
I was very lucky to have a PhD advisor who did all her own experiments, analyzed all of her own data. And so a great side effect of this was that we were left to our own devices, and so we had freedom to do what we wanted.
So, Paul, Alivisatos, you science, obviously your main thing, but you also happen to be president of the University of Chicago.
Indeed.
And that gives you a kind of unique insight from sort of both sides, as it were. How do you give the best advice for young scientists, and how do we create this safe space for them that they can come up with ideas, but actually they're given the funding so that they're not in this constant round of grant application and insecurity, which actually erodes their freedom to think.
Well, look, I'd say a couple of things about that. One is that even for beginning scientists, they're part of a community. And the communities that we build inside these great universities, which are being described here, are very, very special places. You alluded to the atmosphere at MIT. I think, Doris, you would experience that at Berkeley. I think the young scientists at Chicago, Northwestern. they'll all feel that they're, hopefully they're feeling like they're part, or increasingly as they are there longer, they'll feel like they're part of that community because, in fact, these prizes that celebrate individuals, they also celebrate the institutions that foster them, the communities that foster them. And it's very important. On your topic of support, I do think it's a struggle because people want, the people who are supporting science, who are funding it, inevitably are hopeful that there'll be a clear result. And increasingly, as a consequence, they want to determine that it will be there. It's like an investor who wants to make sure that every stock they invest in is going to be a huge success. And so periodically, we'll see these efforts to try to be much more in control and say, okay, I'm going to give you this money and you're going to produce these results. And that's a disaster, right? That doesn't work at all. So I think it is incumbent, and universities, funding agencies, philanthropists, the most important things that they can do is to step back and say, how can I enable the talent that we're working with to take a risk? And that means that they'll fail sometimes, often. But how can I encourage the risk and not try to predetermine the outcome?
I mean, Bob, you famously had an enormous number of PhD students through your lab. How do you encourage them? What's your advice for young scientists? Is there a Bob Langer pep talk on the first day?
Well, I mean, I don't know that there. I mean, my feeling is people have come to our lab because we do things with science, but also it's science that ultimately I think they view might help people. And I think so you have hopefully a double benefit. I'm speculating because I'm not one of the people that have come to my lab, but I think there's a potential double benefit, right? That you could do ideally fascinating science on, say, nanoscience or other kinds of things, and that maybe someday it'll improve people's lives. So I try to get across, I suppose, those kinds of things that what we're trying to do is do things that will be very helpful, be very important, and I also, and this is something I watched when I was actually a postdoc from Judah Folkman, who was my boss, is what I'd call positive reinforcement. In other words, I don't try to, yell at people or anything and say, boy, you're not working hard enough. I just try to want people to feel that they are going to work hard because they want to, because they feel that they'll learn something, they'll discover something, and they'll do some good.
And Chad, a lot of people, particularly in your area of nanoscience, there are commercial applications. And do you feel that they feel that they must then go into a commercial application?
No, not at all. I mean, in fact, when I train my students, I tell them, let's not focus on technology development. That'll come. Let's figure out something the world doesn't already know. Let's learn something. And if you learn something, that will almost always lead to new technology. So I really preach the opposite, even though we're known as one of the big translational labs in the world. But I lead with the science first and then follow with the technology second.
And Sara, in your field, it's not even blue skies research, it's black skies research. It is arguably the most esoteric of the prizes. But what is it that you try to convey to your students or school children who look at your work and like Dave was watching Star Trek and back in the day?
Well, it's more general in that I try to encourage people to find a passion, to find something you love doing that you're also very good at, and to take it away from there.
It's funny, isn't it? Though here we are, we're all scientists, and yet actually at the bottom of this all, it's about emotion and excitement and creativity. Find something you're really passionate about and pursue that.
Well, thank you all for coming and sharing your stories with us, and congratulations to all of you for being the 2024 Kavli Laureates. May your work inspire, drive knowledge, and spread trust in science. That is it for us here in Oslo. Thank you to the Kavli Foundation and to the Norwegian Academy of Science and Letters.
And we hope that you listening to this have been inspired and encouraged by what you've heard. And who knows, perhaps amongst you is a Kavli Prize scientist of the future. We do hope so.